will proceed now with the last presentation from this section. Daniel Fosgerian, Emma Kimse from Palestine, Computer Engineering Department, and Burcu Bakir Güngör and Malik Youssef from the Turkish University and Abdullah Gül University. Score TNT, Enhancing Text Next Topic with Classifier Reverse and Assemble Topic Scoring for Text Classification.
Okay, hello everyone. My name is Daniel Foskerjian, and today I'm honored to present to you our research paper entitled Score Tent Enhancing TextNet Topics with Classifier Diversity and Ensemble Topic Scoring. Actually, I'm from Al-Quds University in Palestine. So, as a brief introduction, nowadays we are witnessing a rapid growth in digital biomedical and healthcare related text, including biomedical literature, clinical notes, healthcare records. While manual categorization is feasible for short text collection, however, it's no longer practical for large-scale text corpora because it requires considerable time and effort and remains vulnerable to human error. Consequently, automated categorization approaches based on machine learning becomes essential as it enables more consistent and scalable handling of large volume of data. However, building machine learning models for textual data specifically is still challenging, as textual data usually represented as a document term matrix where each term contributes to a dimension. This often results into sparse and high-dimensional data, which can increase the computational cost and can increase the risk of overfitting. And this issue is especially relevant to the biomedical domain, where we have specialized terminologies and large vocabulary in common, and the need for accurate and interpretable models are needed. This is where feature selection comes into play as a key pre-processing step in text classification. Its main goal is to identify a compact subset of highly discriminated features that best represent by themselves the whole data. By removing irrelevant, redundant, noisy features, it tends to reduce the dimensionality, lowers the computational complexity, and enhances model accuracy and generalization. In this context, recent work has suggested the exploration of topic modeling in text classification as a semantic feature reduction strategy. Topic modeling is an unsupervised machine learning algorithm that tend to infer latent semantic structures within the textual corpora without requiring any document label annotations. The semantic themes are usually represented as document topic proportions, which describes the distributions of topics within each document, and the second byproduct is the topic word distribution, which describes the representative words per each topic. While the first one is widely utilized in literature as features for document representation, the usage of topic-specific features as a basis for feature selection remains less explored in the current literature. And building on the latter approach, TextNet Topic was introduced as a novel topic-guided framework for text classification, building on the grouping, scoring, and modeling approach. Instead of treating words as independent features, it tends to organize terms into semantically related feature groups. This way, it tends to preserve the contextual and the semantic relationship among related words. By holistically evaluating each topic through topic discriminative measures, it tends to identify the most informative topics for downstream classification. However, one key note to observe here is that TextNet topic uses random forest-based performance as a default criterion for evaluating topic discriminativeness. However, relying on a single learning algorithm may introduce model-specific bias into topic scoring, as different classifiers could capture distinct structural patterns and may assign varying importances to the same topic group. From this observation, it has motivated us to extend TextNet topics and propose score 10. Instead of relying on a single classifier, we use heterogeneous classifiers in the topic scoring component as well as an ensembling strategy to provide more stabilized estimate of topic importance. So let's move to the score 10 methodology in detail. Score 10 usually consists of four main components, the T, G, S, and M. Regarding the T component, it utilizes the latent Dirichlet allocation and applies it on the pre-processed dataset to produce two main byproducts, as I have said earlier. However, in this research, we will use mainly the first byproduct, which is the topic word matrix with M words per topic for subsequent stages. In the modeling, in the G component, it takes as an input the topic word matrix alongside with the training document term matrix to produce K topic-based subdata sets. Each topic usually transformed into a subset by constraining or restricting the X train to hold only the columns that corresponds to the features that resides in that topic. Also here, until we build K topic-based subdata sets. However, one thing to note here is that we retain also the class label in order to provide a supervised evaluation for those topics in the next stage. Okay, in the S component, it tends to evaluate the topic discriminative ability by using its corresponding topic-based subdata set. For instance, here the data set is subdivided into two parts, training and testing part randomly. The training part is used to train a machine learning algorithm, while the testing part is used to evaluate the model. This is repeated for K times using the Monte Carlo cross-validation approach until we get the mean performance metrics. One may use one of those measures based on the classification task at hand as a topic score. This will be repeated for K times until we get a score per each topic, and we then rank them accordingly. As I have said earlier, TextNet topic usually uses random forest as a single learning model. Here we use heterogeneous classifiers, including logistic regression, SVM, random forest, gradient boosting, and XGBoost. Each will produce a topic score, and to provide a stable estimate, we have used equal weight averaging to reduce the model-specific bias and provide a more stable topic relevance estimate. In the final component, the M component, it takes the ranked topics in an accumulated order and try to produce a reduced document representation. For instance, per each cumulative order, we take the union of those accumulated topics and put them into a word set. Then we try to restrict the X train to hold only the columns or features corresponding to the words in the word set, also the X test. Then we train the random forest model in the M component. and evaluate the model. This will be reported in this table, the output table. After we finish all the topic subsets, we will obtain this performance table, and we will select the topic subset, the optimal one that produces the maximum performance to train our final classifier. Okay, in order to evaluate our proposed approach and compare it with text-net topics, we have utilized 4 publicly available data sets: the light-COVID, the World of Science, the CAMDA, drug-induced liver injury, and the multi-label. We have used here the title and the abstract content, and all the data sets were restructured into a controlled binary classification task. Regarding the experimental results, these 4 figures correspond to the 4 data sets at hand. As we can see here, each figure represents the F1 score across progressively accumulating top ranked topics. In order to gain insights from these figures, we have first examined the overall impact of scoring learner in the average view. This table actually shows the F1 score averaged across the topic 1 till top 10 accumulated ranked topics. The statistics here, the standard deviations are computed over 10 MCCV runs. According to these tables, we can see that the average differences between scoring learners are modest. For instance, regarding the World of Science, we have this mean best worst F1 gap, 0.61, and the CAMDA with 0.55, while the light coverage shows the smallest sensitivity. This can indicate that on the average view, there is a limited impact on the choice of the classifier on the F1 score, the final performance. However, this does not mean that the scoring learner is always unimportant, because if we look here at the most sensitive accumulated top ranked topics count with the maximum F1 spread, we can see clearly it has a large importance. For instance, regarding the World of Science, we have a maximum F1 spread at the most sensitive topic count. I think we had 3 topics with 4.54, while the CAMDA reached to 3.29 with large effect size. However, the light covered remains insensitive to the changing of the scoring learner. Overall, these results indicate that the choice of the scoring learner becomes more important when the model is trained on a limited amount of topics, or when we have a selective subset of topics rather than the full topic space. Regarding the ensemble scoring, also here we have it has consistently performed in a stable way and in a competitive way with other algorithms and mitigate the worst case scenario. One final thing to note from all the figures that they follow a clear trend. As we increase the number of accumulated topics, we gain an increase in the F1 score until we reach to a stabilizing point with small fluctuations. This actually indicates that the initial topic contains the most discriminative complementary semantic information, while the later topics usually holds only marginal information or redundancy. As a result, accurate rank